Hello guys, welcome to the channel. In this particular video, I will explain the problem Santa Banta. So let's see the problem statement. Okay, so here is the problem statement. A long story is given here. Let me explain the problem in short. So the problem says that we are given n girls and our task is to find a girl with maximum connections. But hold on, what are the connections here? In order to understand the connections, we are given a 2D array where the size of array is m cross 2. M is basically representing the number of connections, and this 2 is representing that for each row we have two values. The first one is, let's say, x, and the second one is y. So this value represent that the x is connected to y, or these are connected to each other, right? Okay, so this is how the connection is represented, and we are given m connections like this. And our task is to find a girl with maximum connections. In order to finalize a girl, we need to find the kth prime number. So k is basically the size of largest group of girls. So let's say we have like k as the largest size of group, right? So we need to return the kth prime number. Fine. Now, one example is given here. Let me explain the problem with example. So we are given like these connections. Girl, we have total 10 girls and we have 6 connections. So first connection says that girl 1 is connected to girl 2. These are connected to each other. Similarly, we have 2, 3. 2, 3 basically representing that 2 and 3 are connected to each other like this. Okay, and one more thing is there is one interesting relation which is given here. It says that if girl A knows girls B, so knows basically means we are talking about the connections. So if girl A and B are connected, and then B and C are connected, then girl A and C are also connected, right? So this is something which is known as transitivity in relations. So like these two are also connected here. Now it says that consider 1 as the composite number. Okay, so 1 is basically known as a composite number. This is something that we already know. And for pre-compute function, okay, so we are given pre-compute function in the template. Fine. Now it says that girl 1 and 2 are connected, then 2 and 3 are connected, then 3 and 4 are also connected. So 3 and 4 are connected. And if 3 and 4 are connected, then 2 and 4 are also connected, and 1 and 4 are also connected, right? Fine. Also, it says that 4 and 5 are connected. So if 4 and 5 are connected, then 2 and 5 are also connected, then 3 and 5 are also connected, and 1 and 5 are also connected. So this is how the connections are given to us, right? Fine. Now, one more is 6 and 7 are connected. So girls 6 and 7 are also connected, and 9 and 10 are connected. So 9 and 10 are connected, right? So we are given three groups here. You can see that 1, 2, and 3. We have three groups, and out of three groups, the first task is to find a group with maximum number of girls. So you can see that here we have 5 girls, here we have 2 girls, and here we have 2 girls, right? Okay, so we have found the group with 5 girls. This is the group of maximum size, and in order to finalize a girl, we need to return the kth prime number. How to return the kth prime number? So if I try to write all the prime numbers, so I will have 2, then 3, then 5, then 7, then 11, then 13, and so on, right? So what is the fifth prime number? 1, 2, 3, 4, 5. So 11th is the fifth prime number. So our task is to return 11 here, and you can see that the 11 is output here, right? I hope you have understood the problem statement. Okay, so it's a bit complicated to understand, but you can rewind the video in order to understand this problem. Now let me talk about the solution. So after looking at the problem, there are two questions that will come to your mind. The first one is how to find the group of maximum size. You can see that we are given the connections and we have found the group with maximum size 5 here, like, right? And the second question is how to get the kth prime number. You can see that we have generated a list here and then we have written the kth prime number. So these are the two questions that we have to solve. Once we have solved these two questions, then the task is simple. First, find the group of maximum size. Once we have found the group, second task is going to be like returning the kth prime number. So this is how we can solve the problem. Let's start with the first task. The first is finding the group of maximum size. Okay, so in order to explain this, I have to write the same like connections that we were given in the example. The connections were 1, 2, then we have 2, 3. After this, okay, let me see here. So after this, we have 3, 4, 4, 5, 6, 7, 9, 10. Okay, so we have 3 4, then 4 5, then 6 7, and then 9 10. These are the connections which are given to us. Now what we can do is, first of all, we can form a graph using these connections. So the graph will be something like this: 1, then 2, then 3, then 4, then 5, and after this we have 6 and 7 and 9 and 10. So if you consider this whole thing as a graph, then you will find that this is a disconnected graph, right? Disconnected graph. And the concept that we can use here is finding the maximum size of component in a graph, right? So let me write this as well. What we can do is we can write find the max component size in a graph. This is what we can do. The question is how to find the max component size. You can see that the max component size is here 5, right? Because we have 5 nodes connected to each other. And after this we have a disconnection between 5 and 6, and then we have 2 nodes connected, and finally we have 2 more nodes connected, which is 9 10. Right. So how we can find the size of maximum component? In order to do this, what we can do is we can perform the DFS in this whole graph. So first of all, we will perform the DFS, then we will end up here, like we will start with this node. Okay, so let me show it. I'll start DFS from this node, right? And from this I will go to this, then I will go to this, then I will go to this, then I will go to this particular node. So this way I will traverse 5 total nodes, right? I can keep track of this in the DFS function. If you guys are aware of how DFS works, then it is not a big deal to keep track of the number of nodes, right? So after this, when I perform DFS from 1, so I will have a disconnection, so I will end up here. After this I will traverse all the nodes. So you can see that 6 node is still not visited, so I can again start DFS from this particular node. This way I will be able to traverse 2 nodes, and after this there is one more node which is not visited yet, so I can again start DFS. How to implement this? Let me show you. So first of all, let me select this and make this smaller so that I can store it somewhere. Okay, so I want to store this thing over here. Now let me show you how we can implement this thing. In order to implement this thing, I can write the code. So I'll write something like this: for I equals to 0, I is smaller than let's say I have n nodes, so I'll do something like this: I plus plus. Okay, and you can see here that I will start from 1 actually. So let me remove this and I'll write 1 here. So I'm starting from 1 to n, right? And I'll start from this node. After this I will when I perform DFS, then all these will get visited, right? So I can call if my visited, I have to keep track of visited as well. So if my visited of I is equal to 0, in that case I can perform DFS. What's special from I? What's special about this code is, you can see that first of all 1 is not visited. So after this when I perform DFS, then all these nodes will get visited. So it is not going to perform DFS for 2 3 like this, right? So after this it will perform DFS directly from 6th node because it is not visited yet. So this is how it is going to work. This means that for this particular graph, DFS function will be called 3 times, right? How to call DFS function? So for this we can do one more thing. We can initialize a counter here. So let me take green color. So I can have a counter here. Counter is basically equal to 0 at the starting, and after this when this DFS completes, so I will have all the values counted while traversing the graph. So when I do this, then I can keep track of max count as well. So max count is going to be max of max count comma the current count that I have. This is how I can get the maximum size group, right? This is how we can get. Now the question is how to perform DFS. So in order to perform DFS, the task is quite simple. I can write a DFS function, a usual DFS function, but the only difference is we have a counter here. So I have I, then I have adjacent list, and there are some cases where we have to form the adjacent list, and there are some cases where we have already given this list. So that's not a big deal. I will show you that particular thing in the implementation. So I have I, then I have adjacent list, then I have count, right? And I have one more thing which is visited. What I'll do here is, first of all, I will check one thing, that this is how we write a DFS function. If my visited is equal to true, right? If already visited, then I can simply return. And if it is not visited, then I can mark visited as true. Visited of I equals to true here. This is something that I can write, right? Okay, after this, see, we are traversing one node in DFS function, so I can increase the counter. And just after this, let's say I have one, then I have two connected and three connected and four connected, like this, so, and five connected. So we are going to jump to any particular neighbor, right? So let's say I go to this four, then after this four I'll go to this five. So how to implement this? This is a simple recursive call. For this I have to call all the neighbors. So for every neighbor x in adjacent of I, this means that for the neighbor of current node, which is I, right? For every neighbor we can check if my visited of x is equal to false or zero, whatever you say, then we can call the DFS. Then we can simply call the DFS from x itself. Then we have adjacent, then we have count and visited, right? This is how we can write the visited function. So once we have the DFS visited function, after this we can simply keep track of the max count. Okay, so this is how we can get the max size component. The question is it only the DFS function that is going to give us the answer? No, we can use the BFS function as well. The main goal is to traverse all the nodes, so it doesn't matter whether you use DFS or BFS to traverse all the nodes. Once you have traversed all the nodes, then you can simply get the count, right? So this is how we can get the count of every like maximum component size. Now let's talk about how we can get the kth prime number. So let me write the heading here: kth prime number. Kth prime number. In order to get the kth prime number, we can simply use the sieve algorithm. If you guys are aware of sieve, used to like get a list of prime numbers in a more efficient manner. So the complexity is generally n log of log n, something like this, right? So this is how we can get the prime list of prime numbers. So the list will be like 2 3 5 7 and so on, right? How we can do this? The task is quite simple. Let's say I have a list which is initially filled with false values. So I'm going to explain with a size 5, right? So I have 5 false values. False, then I have false, then I have false, right? Okay, so now what I can do is, even let me increase the size first. So 1 2 3 4 5 6, then false 7, then false 8, then false 9. So I have 9 values, right? Okay, so I can start a loop for I equals to 0. Even let me tell you the concept. So implementation is quite simple if you guys know the concept. I know one thing, that if we have a number 2, then all the multiples of 2 are never going to be a prime number, right? For example, if I have 2, then 4 6 8 10, then I know one thing for sure, that all the multiples of 2 are never going to be a prime number. Why I'm saying that? Because these number will have at least one divisor, which is 2 itself, right? So these are never going to be a prime number. Similarly, the multiples of 3 are not going to be prime number. So like I have 3 6, then 9, then 12. So you can see that 6 9 12, all these have at least one divisor, which is 3. So that's why I'm saying that. So what I can do is, I can check from 1 to n. I can check, okay, not from 1, for actually 2. 1 is actually an exception, because if I go to the table of 1, then I will have 1 2 3 4. So I can't start with 1. So for 2, I can get the multiple of each prime number, and I can make those value true. For example, for 2, I'll start from 4, 2 into 2. I'll start from 2 into 2. So you can see that 1, 2, 3, 4. This is value is going to be true now, right? And 6 is also going to be true now. And then 8 is also going to be true now, right? And for the table of 3, so 1, 2, 3, 4, 5, 6. So I'll make 6 as true, I'll make 9 as true, right? And what about the table of 4? So for 4, you can again see that I'll start from 4, then I will make 4. Okay, so 4 start from here. I will make 4 as true, then I'll make 8 as true. This is how I can make. when this loop completes, then all the false value will be prime number. So 1 is never a prime number, 1 is an exception. You can see that 2 is a prime number, 3, 2, 3. Then I have false value here, 5 is a prime number, then I have 7, right? This is how we can get the list of prime numbers. Talking about the code, so the code is quite simple. Let me write it quickly. So for I equals to 2, then and then I plus plus. This is how we can write. After this, I will have 4, j equals to I cross 2, then j is smaller than n, then j plus equals to I. This is very important step because each time we are going through the multiple, right? If you have 2, then I will have 4, 6. This is how I will move 8, then 10, right? So that's why I am doing j plus I, and after this I can simply do prime of j equals to true now. And just remember one thing, that all the false value will be our prime number. So this is how we can get the list. Once we have got the list, so we just need to do one thing, that we will get the maximum group size from here, right, from this particular code. So let's say max is the max group size, so I simply need to return primes of max. I hope you have understood the problem. So what is the complexity here? The complexity is simply going to be, you can see that in DFS the complexity is nothing but V plus E, right? And in, since the number of node is n here and the connections is m here, so n plus m is the complexity. I hope you are able to understand this thing. So this is all about this video. Let me show you the code here. Okay, so here is the code. I have written the Java code on the left hand side and C++ and Python code on the right hand side. You can see that the first task is to fill the pre-compute function. Why it is called pre-compute? Because I want to compute the list of prime numbers only once, right? So once I have computed, then I can use it anytime. So I have made a store array, then I have picked all the elements using the sieve algorithm. So this is the point where I'm using the sieve algorithm. Why I have taken this particular size? So there is a reason. The reason is, let me explain the reason. I have taken the size as 1299723. Even I remember this value. The reason is, what the maximum value of n that we can have according to the problem is 10 raised to the power 5, right? So if you are given values, so in worst case it is possible that we have all the values connected, so we have 10 raised to the power 5 connection, right? And in that case k will be 10 raised to the power 5, and we need to return this particular prime number, the prime number at this place. So the prime number at this place is going to be 1299722. This is the prime number, this is the 10 raised to the power 5th prime number, right? And that's why I have taken the size as this plus 1. So this is the reason. And now you can see that I have filled all the like array. This is the array of primes, and once we have the false values, then I can simply return all the prime numbers only in this particular list, which is primes. And I have done the same thing here. The same thing is done here and in the Python code as well, right? So now once you have understood this, then this is the main task that we need to do. We have a DFS function, and then we are calling the DFS function. In Java, the adjacent list was not given to us. We have to calculate the adjacency list in order to create the graph. But in C++ and Python, we are already given the adjacency list. So that's why I have not calculated it here. You can see that we have just written the DFS call here. And the same thing is written here. So I hope you have understood the problem and the solution. The problem was lengthy to read, but the solution is quite simple if you guys are aware of the graph concept and the DFS. So this is all about this video. Thank you. If you guys like the explanation, then you can hit the like button. If you are new here, then you can subscribe the channel. So thank you.